These are notes from Melham's Math 60 for Wednesday, April the 22nd, section 9.2, page 771. Today we're dealing with something called one-to-one functions and inverse functions. Okay, you might recall in order to have a function, it was true that 1x could give you only 1y. So quickly I put 1x, 1y. It also satisfies something called the vertical line test. If you draw a vertical line on a graph anywhere, it will touch at only 1 point. If you look at 27, 29, and 31, which I've pasted over here, these are all functions because they all pass the vertical line test. Then for something called a one-to-one function, and I will abbreviate one-to-one with a 1-1, it's a little bit easier to write than O-N-E-T-O-O-N-E. In order to have a one-to-one function, you still have a function, so both of these have to apply, but in addition to 1x gives you 1y, 1y can only give you 1x. And that leads to something called the horizontal line test. For a one-to-one function, it would pass something called the horizontal line test, which means if I were to draw horizontal lines anywhere, it would touch at only 1 point. Okay, for problem 19, it asks, is the function one-to-one or not one-to-one? I'll have to know something about the graph. So f of x equals 2x. We know that looks like y equals mx plus b. Quick and dirty graph is that it's a line like so. And yes, it is a one-to-one function. It's a function because it passes the vertical line test, but it's a one-to-one function because it also passes the horizontal line test. If I draw a horizontal line anywhere, it's only going to touch at 1 point. Problem 23 asks, is it one-to-one or not? F of x equals negative x squared plus 3x. Well, I know it's not going to be one-to-one because from earlier work, I already know that this is a parabola opening down. We could draw the graph very carefully, nitty-gritty details, but we don't need to. I know it's a parabola looking like that, which is a function. It passes the vertical line test, but you can tell it's not going to pass the horizontal line test. I can draw a horizontal line which will touch at 2 points, so no, this is not a one-to-one function. Problem 25, they just give you a list of points, 1, 1, 2, 1, 3, 1, 4, 1. Again, this is not one-to-one. It's not a one-to-one function because 1y has many x's. In order to have a one-to-one function, not only does 1x give you only 1y, but 1y can only give you 1x. But if I say y is equal to 1, in this case you have many x's. If y is 1, x could be 1, 2, 3, or 4. Incidentally, this is still considered a function because for any x that you pick in the domain, there's only going to be one y. So if I say x is 2, y can only be 1 and nothing else. If I say x is 3, y is 1 and nothing else. So that is a function but not a one-to-one function. Okay, then 27, 29, and 31 ask if they are one-to-one functions. Notice again, they're all functions. They all pass the vertical line test. 31, it might be kind of hard to tell what's going on, but you have this horizontal line here down at y equals negative 4, it looks like. So they all pass the vertical line test, so they're all functions. But do they pass the horizontal line test? So 27 is one-to-one. If I draw horizontal lines anywhere, it's going to touch the graph in only one spot. 29 is not one-to-one. It's a parabola opening down, which is sort of like this one. It does not pass the horizontal line test. And 31 is also not one-to-one. It might be kind of hard to see, but the graph is a horizontal line. So it does not pass the horizontal line test because if I draw a horizontal line right over the horizontal line, then it touches at more than 1 point. In fact, it touches at infinitely many points. All right, then starting with problem 35, they ask you to find the inverse of the function. So they give you f of x equals 2x plus 4. Okay, so now we're doing something called inverse functions. The inverse function is kind of like the undo function. It undoes a function. It turns out that one-to-one functions have inverse functions. So if a function is not one-to-one, it does not have an inverse function, but the one-to-one functions have inverse functions. It's sort of like the undo function. The way we write inverse function is f with a negative 1 of x. So we say f inverse of x. This is not an exponent. This does not mean 1 over f of x. It's a different thing altogether. Right? So this f with a negative 1 and x means the inverse function. It's sort of like the undo function. How do you find that? So f of x equals 2x plus 4. So first you call this letter y. Y equals 2x plus 4. And now you switch x and y. Every time you see x, put y. Every time you see y, put x. You just switch them around. X equals 2y plus 4, so you switch x and y. And now you just go back and solve for y once again. So solve for y, subtract 4. X minus 4 equals 2y. Divide by 2. And y is isolated. Quite often it ends up being on the right side, but we like to put the y on the left side. So y equals f inverse of x. So they want you to write this f inverse of x. I want you to be comfortable writing that also for quizzes or tests. write the f with a negative 1x is x minus 4 over 2. Here's another example here in 41. The given function f of x is 2 over x minus 3. They want you to find the inverse function. Okay, so again, call this y equals 2 over x minus 3, and then switch around x and y. So whenever I see y, I put x. Whenever I see x, put y. X equals 2 over y minus 3 is the function. Now solve for y. So that's what it originally was. And now to clear up the fractions, I'll multiply both sides by y minus 3 in green. So that cancels out, giving me 2. Multiply this by y minus 3, I get xy minus 3x. And now I want to solve for y again. So add 3x to both sides. Xy equals 3x plus 2. And then just divide by x. So y equals f inverse of x is 3x plus 2 divided by x. Okay, then for 51, find the inverse function. F of x equals 2x cubed minus 3. Same process, call this y. Y equals 2x cubed minus 3. And then switch around x and y. So wherever I see y, call it x. Whenever I see x, call it y. And now resolve for y. So isolate the y. So I'll add 3 to both sides. X plus 3 equals 2y cubed. Divide by 2. X plus 3 over 2 equals y cubed. And to get rid of a cube, you do the cube root of both sides. So cube root, and again, y is isolated on the right, but I'm going to put it on the left. So y equals f inverse of x. I want you to write the f inverse of x is the cube root of x plus 3 over 2. Then in problem 55 and 57, I believe also, they're asking you to show that f and f inverse are inverses. So what does that mean? They give you the function f of x is 2x plus 9, and the inverse function is x minus 9 over 2. Why are they inverse functions? That means whenever you do f composed with f inverse, you do f of f inverse, you get back the original x again. And likewise, if you do f inverse of f, you also get x. So it is indeed an undo function. When you do one and you do the other, you get back to where you started from. So here's how you do f of f inverse of x. So f of f inverse of x means f of, and then inside the parentheses, instead of writing f inverse of x, I put down what it's equal to, x minus 9 over 2. And now this mess behind my pen goes into the function f. 2 times that mess plus 9. So 2 times x minus 9 over 2 plus 9. Notice the 2's cancel out, such as if x minus 9 plus 9, which is indeed x. So that means when I do f of f inverse of any number, I get the original back. Likewise, do f inverse of f of x. So f inverse of, inside the parentheses, f of x, I'm going to put down what it's equal to, which was 2x plus 9. And now again, this thing behind my pen goes into f inverse. So that mess goes right there. So 2x plus 9 minus 9 divided by 2. Notice the 9's cancel out. So I have 2x divided by 2, which again is x. Okay, so that's the end of the proof. So f of f inverse of x is x, and f inverse of x of f of x is also x, which means whenever I do f with f inverse, I get back the original. So they are undo functions. One function undoes the other. Finally, 61, they ask you to find the inverse and then graph to show the relation on a graph. So f of x equals 4x plus 3. So put y equals 4x plus 3. Switch around x and y. X equals 4y plus 3. Solve for y, subtract 3. X minus 3 equals 4y. Divide by 4, except put y in the left. So y equals f inverse of x equals x minus 3 over 4. And they want you to graph them on the same graph. And so for the original function, I know when I plug in 0, I get 3. So 0, comma 3. And just to get another point, I plug in negative 1. When you plug in negative 1, you get negative 1. And I know it's a line, so 2 points determine a line. So in green, I have the original f joining negative 1, and 0, 3. For the inverse function, I could plot points, but I just realized, well, I can just switch around x and y's. So if I switch around 0, 3, I have 3, 0. And if I switch around negative 1, I get the same thing. So in red here, I just connect those, and I have in red f inverse. So that's the inverse function. Okay. And then they want you to draw the line of symmetry. The line of symmetry for a function and its inverse is always y equals x. Okay, so y equals x is sort of a mirror image. So if I kind of pretend this is a mirror, the mirror image of the green is the red and vice versa. So if you look at this part here, the reflection of this across the pen that I have would be over here. And the reflection across the red here would be the green here. And so that's a characteristic of inverse functions, that one would be the mirror image of the other across the line y equals x. Okay, so this is Melham's Math 60, Wednesday, April 22nd, section 9.2, page 771. So tomorrow we will go on to section 9.3.